We have one last thing to talk about with respect to Gaussian elimination, and that is how to use Gaussian elimination to compute the inverse of a matrix. What we do is we apply a bunch of row operations to convert the matrix to the identity, and then if we apply the same row operations to the identity matrix, it converts it into the inverse. Isn't that interesting? How does that happen? Well, remember that row operations are given by multiplication on the left by a matrix. So let's look at this first set of row operations, which converts A to the identity, and let's call that matrix M. So what we have is that M times A is the identity. Okay. Well, let's apply M to the identity. And, well, obviously M times the identity is M. Well, this first equation tells you that M, of course, is A inverse. And the second equation says that when you apply M to the identity, you get M, which is to say A inverse. And that's how it works. It's quite simple. So let's look at a quick example of this. Let's take the matrix like this, 1, 1, 2, 1, and we put it next to the identity, and we apply this operation to convert it into, the first row stays the same, and the second row turns into this. And now we apply a new kind of operation going back in the other direction. We haven't used this kind before, but it's the same basic idea, to kill that 1, which makes the matrix A turn into this, which is almost the identity. And then finally we just have to multiply the last row by -1 in order to convert this -1 into a 1. And when we apply that operation, on the right hand side what we get is -1, 2, -1. And so what we've computed is that the inverse of the original matrix is this matrix, -1, 1, 2, -1. We're going to go on now to chapter 2, which is the study of vector spaces. This is a significant part of this course. The notion of an abstract vector space is something that's probably not familiar to most people. Many people are familiar with Rn, and a lot of what we do in this course is just redoing everything that's familiar to you in Rn in this context of what's called an abstract vector space. So let's discuss that a little bit now. So what is a vector space? Well, all we know about is Rn, so let's talk about that. What is Rn? Rn is a set of n tuples, and we call these vectors V, and it has a bunch of operations. Well, it has 2 operations on it. You can add 2 vectors, and you can multiply a vector by a scalar, or a number. It's called scalar multiplication. And these 2 operations have a number of properties. So I'll write down a few of these properties. So for example, addition of vectors is commutative. V plus W is the same thing as W plus V. And it's associative. V plus W plus Z is V plus W plus Z. It has a 0 vector. If you take all zeros, you add that to any vector, you get 0. And scalar multiplication is distributive. And there's a few more of these. Well, a vector space is just an abstraction of this setup. It's just something which has these properties. It's sort of modeled on Rn. And so let's talk about that a little bit. So this is really the crux of the course. Everything we're doing from now on it's sort of a question of point of view. There's Rn, which you're familiar with, and now you need to learn to think a little bit more abstractly. Here's an abstract definition of an abstract vector space. And a vector space, it's a set, it's a collection of objects. We call them vectors. And these come with two operations. You can add them. If you have two vectors v and w, you get a new vector called v plus w. That's vector addition. And if you have a vector and a scalar, remember a scalar is a number, you can multiply the scalar times the vector and get a new vector. And these operations are required to satisfy 8 properties. The commutative property, the distributive property of addition, there's the 0 vector, there's the negative vector which you can add to get 0, you can multiply a vector by 1 to get it, it gives it back itself, and then there are these last 3 properties of scalar multiplication. And these are the properties that Rn satisfies, and we've just written them down in what we call a vector space, or an abstract vector space, is something satisfying these properties, and we use the word abstract to contrast it with the concrete vector space that we're all familiar with, which is to say Rn. So here's an example of a vector space besides Rn. Take the 2 by 2 matrices. You can add any 2 matrices, and you can multiply them by a scalar, and all of the usual all the requested properties hold. You can multiply 2 matrices, but you should ignore that for the purposes of this example. We come now to an example which I think is quite helpful in getting your brain around the notion of an abstract vector space. So the example is the following. You consider the following set of functions. We define a vector space to be the following set of functions. It's those functions f such that the second derivative of f is equal to minus f. So that's a set. It's a collection of functions. So what's a function in this set? Well, cosine of x satisfies this property. The derivative of cosine is minus sine, and the derivative of minus sine is minus cosine, which is to say minus f. And also sine of x satisfies this property. And the key point is that if you take any multiple of cosine of x plus a multiple of sine of x, it also satisfies this property. So that is to say that you can add these things and you can multiply by scalars. And that's what's required of a vector space. If you add any 2 of these functions and you multiply by a scalar, you stay in the same space. And it's easy to see that all of the requested properties hold. So this is an example of a 2-dimensional vector space, but it's not obviously related to Rn or R2 or anything in some elementary way. It's kind of a new kind of example. And it's a natural example. It's just this, it's a differential equation. It's the set of solutions to a differential equation. So let's talk next about subspaces. Suppose I have a vector space and I have a subset of the vector space, just any subset of the set. We say that W is a subspace if W itself is a vector space. And what does that mean? So V is a vector space. We have a subset. I'd like the subset to be a vector space. Well, you use the operations from V, and the only question is, if I take 2 vectors in U and I add them, well, that's a vector in V, but it's not necessarily in W, and so the requirement is I have to require that. And also, if I have a scalar and a vector and I multiply them, again I get a vector in V, and I require that that be in W. So that's the definition of a subspace. It's one which satisfies these 2 properties. And here's an example in R2. If you take W to be a line through the origin, this is a subspace. If you add any 2 vectors on this line or multiply by a scalar, it stays on the line. Here are a few more examples. Again, let's look in R2. And let's take W to be just the 0 vector. Just the vector at 0. This is a subspace because if you add 0 to itself you get 0. And if you multiply 0 by any constant you get 0. Here's a non-example. If you take something curved. But here's another non-example which is maybe slightly less obvious. If you take a straight line but it's not through the origin, that's not a vector space. Because, for example, if you multiply one of those vectors by 0, you get the 0 vector, but that's not on the line. So here's an important way to construct a vector space. This we're going to use over and over again. So I have a vector space V and a bunch of vectors V1 through VR. Any vectors at all. Just take any collection of vectors from your vector space and let W be the following set. You take A1 V1 plus A2 V2 plus so on AR VR, where A1 through AR are any scalars. This is, in other words, this is all of the linear combinations of the vectors V1 through VR. This is a subspace. So why is this a subspace? Well, if you take one of these vectors, which is a linear combination, and take another one, which is a different linear combination with coefficients bi, well, what happens if you add them? Well, u plus v, you have to ask whether that's in W. Well, u plus v, if you work it out, is clearly A1 plus B1 times V1 plus and so on. And so when you add them, you get another linear combination of the vectors. And something similar happens with scalar multiplication. So here's a picture of what's going on. In R3, you take any bunch of vectors, V1, in this case 3 of them, and you're taking the plane spanned by them. In this case, the 3 vectors all lie on a plane, and so the subspace that you get by this construction is a plane. We call this the span. This construction is the span. So here's another example. Take 2 vectors in R2. What's their span? Well, if they don't point in the same direction, what's the plane spanned by these 2 vectors? It's clearly all of R2. In other words, what I'm saying is that if you take all of the vectors you can write as AV1 plus BV2, you can get every vector in R2 this way. Okay, I think that's a good place to stop. So that's all for now.